Hey guys, Buildzoid here, and today we're going to be taking a look at the core voltage regulation of the ASUS RTX 4070 Ti TUF. I bought this card on eBay, so big thank you to the channel supporters for making that purchase possible. And with that out of the way, let's get into it. Now, for loading the card, I'm just going to be using TimeSpy Extreme, because out of every single workload that I've tried, this is the heaviest one that isn't Furmark. We're not going to use Furmark, because Furmark without a power limit is terrifying. So, yeah, we're going to use TimeSpy Extreme. I have tried Port Royal. It's not heavier. It might be harder on stability because it actually loads the, ray tracing stuff, but it's not heavier from a power delivery perspective. Anyway, so, yeah, we're going to use TimeSpy Extreme. The oscilloscope right now is set to its full 100 megahertz bandwidth, so I don't have any bandwidth limit on the scope right now. And then for how the scope is connected to the card, it's just a piece of coax that is soldered to some of the multi-layer ceramic capacitors directly behind the GPU core. And there's a 50 ohm termination in front of the oscilloscope to prevent any reflections in the coax, because it is just soldered directly to the card. Anyway, also the scope doesn't actually, I'm relatively certain that my scope does have an internal 50 ohm termination circuit, but it's not enabled in software, so I need an external 50 ohm termination. Anyway, that's the test setup here. And yeah, we're just going to run TimeSpy, and we're going to run it first with the card in sort of stock configuration. And then we're going to overclock the card a bit and have a look at how things react to that, and then we're eventually going to disable the power limit, because that, I think, is the most interesting thing that I've noticed with that. Well, I mean, I find it interesting, okay? I'm going to stop trying to justify why I do this kind of testing, because that's a losing battle on my front. Anyway, yeah, so here we are running TimeSpy. You can see that the waveform is kind of wobbling around, and that's the power management doing that. That's not it's not the VRM's fault. That's literally the NVIDIA driver constantly adjusting the core voltage so that the card stays within the power limit. So that's why the waveform keeps moving around. But the more interesting thing to me, and that'll be more visible once we disable the power limit, is these big downward spikes. And right now we're not seeing any, but actually, that one's pretty big. I go to single. We should eventually catch one if it just runs for long enough. And unfortunately, TimeSpy Extreme's graphics test 2 test is, not very consistent. Yeah, so we're seeing, these kind of, these kind of, spikes. And if you zoom out on them, right, that's at 200 microseconds. If you zoom out to, 10 milliseconds, that looks like a really sharp downward spike. But if you zoom in on it, it's it's not really a big downward spike, is it? Right? Oh, well, this one is. Right? Yeah. So with something like this, though, right, we have, this kind of looks like idle, and this looks like it could be an actual, downward transient, and then it sort of recovers, and the noisiness is it's a GPU. GPUs are very, very noisy because they constantly pull different amounts of current depending on what exactly they're calculating at any given moment in time. So yeah, I've not actually seen a quiet GPU workload. There are for CPUs, there are certain workloads that have very quiet waveforms in terms of core volt, or don't produce a lot of transients. And then you have some workloads that produce a lot of transients. I've not really seen that with GPUs. Admittedly, I don't have any really super synthetic, just pure number crunching workloads for GPUs. So maybe those would be a lot more consistent in terms of current draw. But yeah, your typical 3D workloads, they're a mess. So this right here is expected. But yeah, so the main thing that I wanted to capture with this card, and we're not getting it right now, yeah, is these kinds of these kind of weird voltage curves that we're seeing. So, because if you zoom out, right, and you just run the card and you just look at the peak to peak value, This is really bad. Or, okay, that's not true. It's not really bad. But it's nothing, it's not you know, particularly impressive. 200, you know, 80 millivolts peak to peak. And actually, if we zoom out more, you're going to notice that it goes even higher eventually. Now, part of that is just because the entire, like, set point, like, the target voltage for the VRM keeps getting moved around by the power management. And, you know, we can see that in the waveform sort of wobbling around at like 50 milliseconds per division. But even when we zoom all the way in on some of these downward spikes, right, you can see that the spikes are actually kind of very gradual. They're not really, they don't really look like the typical, you know, really hard spike that you expect from like a load insertion transient or a load release transient. And also, yeah, the peak to peak on the stock power, like on the card at stock has kind of a lot of peak to peak. But there's also a lot of power management going on, which is probably which produces a lot of that peak to peak. So now we're going to try overclock the card a bit. And I'm on some old version of Afterburner, so I'm pretty sure that's why the memory clock doesn't go any higher than that. Or at least I hope it is, because otherwise I'm going to have to find a better overclocking utility. And well, hopefully I find something. Anyway, if we max out the memory clock, peak to peak doesn't really change very much. Yeah. So the things still look pretty not great in terms of voltage regulation. If we start raising the core clock, the core clock doesn't change very much. Yeah, so peak to peak still doesn't change. So next we're just going to max out the power limit. And that didn't really change the waveform that much either. Which is, yeah. We're going to overclock the GPU a bit. And this is about as high as it can go without disabling the power limit. And okay, we're still seeing, okay, now we're seeing like 297 millivolts peak to peak. I think if we ran this long enough, yeah, it might eventually start hitting even like 300 millivolts peak to peak. Actually, maybe let's take a closer look at some of what's going on right now. Like, I really want to catch some of these massive downward spikes that we're getting at this point. We're going to have to wait for a little while because, like, the workload load cycles, like, there's a specific section that's really heavy, and we're not in it right now. Yeah, there we go. Now, so something like this, right? I'm gonna have to move this out of the way. So yeah, so this right here, so what's annoying with this sort of waveform, right, is like, okay, so the voltage is like going down gradually, which doesn't really look like a transient. As far as I can tell, this VRM really doesn't have any like DC load line on it, which is expected of a NVIDIA GPU. They generally don't have a DC V-droop, which basically means that the card doesn't ramp down the voltage based on average output current. And the reason, and this is just like a voltage regulation scheme that NVIDIA uses. So anyway, we have like the voltage sort of just coming down here, which I'm pretty sure is a power management thing. And then we get this big upward spike, which, okay, that looks like a pretty typical load release transient. And then the voltage dives down, which looks like a load insertion transient. But the sort of issue on this is like, okay, well, if we want to judge this as a, like from a voltage regulation perspective, is, so where does this spike, like, where does the load insertion spike start and where does it end? Right? Because I'm pretty sure the target voltage is probably this right here. In which case, this is actually not that big a dive, right? Because like if the requested voltage is whatever is at like 950 millivolts, which admittedly is a very low voltage, but yeah, if the GPU driver is requesting 950 millivolts, then the fact that we're bottoming out at like 800 something, like that's, you know, that's like 50, 60 millivolts of undershoot. That's not really that big a problem. So, you know, that makes sort of judging the voltage regulation on one of these cards with the power management running, or at least with the stock power limit, really difficult, because like we get this, and we get a lot of this, right? Like that's basically all of the big downward spikes that we see look something like that if you zoom in on them. And so now we're going to disable the power limit. And something rather interesting is going to happen to our waveform. It cleans right up. Because the thing is, on modern GPUs, the power management is incredibly fast. And this is true for basically all modern GPUs. And like, I would not be surprised if NVIDIA's driver was capable of adjusting the core voltage at least once per millisecond. Because, for example, Ryzen CPUs can do that. AMD GPUs can do that. And NVIDIA was sort of the first manufacturer to come out with like a really aggressive, fast, dynamic boost system back with like the 900 series GPUs. Like 600 series kind of did it, but not really anything that special. But yeah, so NVIDIA's power management probably can update the core voltage at least once per millisecond. It might even be faster than that, but I kind of doubt it. But yeah, really sort of interesting how, like, if you disable the power management, right, and I reset the peak to peak, the statistics, you'll notice that the peak to peak now sort of stays at around 240 to 250 millivolts. Which admittedly isn't particularly impressive in the grand scheme of GPUs that I've ever measured, right? Like, I've seen 980 Ti's manage 200-ish. I've seen 6900 XTs manage 200-ish. R9 Furies can do 200-ish. So yeah, 246 millivolts peak to peak is not really that impressive, though. At the same time, with NVIDIA GPUs, you do have to consider the fact that, like, and AMD GPUs do have some DC load line, whereas NVIDIA GPUs don't. So NVIDIA GPUs inherently will have more peak to peak, even if, like, you can't really compare NVIDIA versus AMD GPU voltage regulation, because they use kind of different voltage regulation schemes, which is annoying, but, yeah, the thing is, I don't have other 4070 Ti's to compare against, so that's why I'm, like, pulling on random other cards that I have measured, because I don't have a reference point for what a bad 4070 Ti would look like. Also, it looks like we just had a frame drop there, which happens. The card's probably kind of on the edge right now. Because 3 gigahertz, especially since the temperature is going up, like we're hitting like over almost approaching 100 degrees hotspot. Like, it's been running for a while. The room's pretty warm, mostly because this GPU kicks out a decent amount of heat, especially once you turn off the power limit. But anyway, yeah, so the voltage regulation isn't anything like crazy in terms of being like really good, but at the same time, it's not terrible. Okay, like, if this was under 200 millivolts, I'd be extremely impressed. It isn't under 200 millivolts, so it's like, okay, this is pretty standard GPU things. At the same time, it's not over 300, so it's better than a lot of other NVIDIA cards that I've measured, but unfortunately, yeah, I don't know how this compares to, like, other 4070 Ti's, which is sort of the thing I'm most annoyed with this video, is, like, I suspect the ASUS TUF PCB has better voltage regulation than every other 4070 Ti out there, probably. Mostly because of the capacitor selection that ASUS has on their card versus everybody else. There might be some cards that get very close to this level of voltage regulation, but unfortunately, without measurements, yeah, that's basically just a guess. I'd like to think that I'm pretty good at guessing which cards have good voltage regulation just based on looking at the PCB, because I have measured an awful lot of cards at this point. So I like to think that I've noticed a pattern in terms of, you know, what component selections lead to good voltage regulation, but without measurements, not really, you know, not great. Well, I'm not satisfied without measurements. Let's just put it that way. Anyway, but what I would like to do now is actually, we're going to zoom in on some of the waveform now that the power management isn't, you know, constantly kicking in, and hopefully, yeah, and now we have what looks like a pretty typical transient. We're not getting that, like, sort of, you know, that wacky curve around the big spike. We're just getting the big spike and... Oops, what did I press? Go away. Yeah, so now we're just getting, like, very sharp downward spikes, which is sort of what you'd expect from a transient. And also, we're now at, like, 20 microseconds per division. Instead of, like, 100 or 50-ish, right? I'm gonna turn the power limit back on. And yeah, and you immediately, well, do we immediately see the difference? No, because I need to, yeah, I need to set the thing lower. Yeah, but you... Actually, maybe if I just run it at, like... Yeah, so you can really see the power management sort of kicking in, like, mid-frame render, where it's like... So your average... And the funny thing is, I wonder if we even see that clearly in the core voltage readout in software. You can kind of see the voltage getting shifted around, but, like... on the oscilloscope, we can see that the core voltage is getting shifted around, like, multiple times within, you know, a few milliseconds, within like 10 milliseconds or something. Whereas GPU-Z right now is monitoring at like, where is it? GPU-Z is monitoring at 0.3 seconds. So GPU-Z does not see the full range of like how much the voltage is being lowered. In fact, based on the oscilloscope, it looks like for some parts of the frame render, the card might be like intentionally lowering the core voltage to like 950 millivolts or something. Yeah, so I thought this was just kind of interesting to sort of see the difference that you get in the core voltage waveform with the power management turned on versus with it turned off, where when you turn off the power management, the core voltage is a lot more consistent because the card isn't constantly trying to minimize its power consumption. And then the other thing is, like, with the power management disabled, we actually have some idea of how good the voltage regulation of this VRM is. Unfortunately, we don't know how good it is compared to other 4070 Ti's, and that's sort of everything I wanted to show in this video. I do plan to mess around, like, because this isn't super, like, this isn't the greatest voltage regulation I've ever seen, I'm going to be messing around with, like, adding more capacitance to the card. Because 250 millivolts peak to peak, I mean, so the thing with peak to peak is that it's very easy to reduce the amount of overshoot. Okay, that is very easy to do. You just put more capacitance right on the output of the VRM, because the upward spikes in voltage, those come from the VRM, from the excess energy stored in the inductors when the GPU core goes from, like, low resistance to high resistance, right? So the current draw, like, the amount of current that's flowing through the core suddenly, like, gets reduced, and, well, now you have a bunch of excess energy in the inductors that needs to go somewhere, it gets dumped into the capacitors. So if you just put more capacitance directly on the output of the VRM, you get better, like, you reduce the overshoot voltage. Which doesn't help overclocking at all, because GPUs crash when the voltage is too low. They don't crash when it's too high. Well, actually, that's not true. They do crash if your average voltage is, like, really high and your temperatures are going sky high, but the like, upward voltage spikes that happen due to the card literally going from high load to low load, like, yeah, those don't cause crashes, generally speaking. So, yeah, while it would probably be very easy to reduce the peak to peak, that isn't really that helpful in terms of overclocking. The card currently just about tops out at around 3-ish gigahertz, at least with the power limit disabled. Without the power limit disabled, it's slightly worse than that. And the reason I say 3-ish gigahertz is, like, let's say I go to 106, and we should start seeing sparklies. Huh. We're not getting them yet. Okay, well, let's go to 115. That's weirdly stable. Oh, I think we're just about starting to see them. Might even see some frame drops, but... yeah, so you're starting to see, like, we're getting some rain... yeah, sparkles showing up on screen. Actually, I think if I turn the power management back on, it's just going to crash. Okay, well, the core clock came down a bit. Stability hasn't really changed. Yeah, so that's going to be annoying. Anyway, power management back off again. But yeah, so in theory, if I manage to reduce the like minimum voltage over here, it might be possible to run slightly higher clocks. And when I say slightly higher, like tens of megahertz. And the really annoying thing with like trying to judge a capacitor configuration with like core clock, like even if you're just like taking a card and adding more capacitance to it, is that the maximum stable clock of a GPU is tied to both the operating voltages and the operating temperature, right? So if you have a slight decrease in operating temperature between test run 1 and test run 2, so like before modifications, it's like, oh, the card maxes out at like, you know, just over 3 gigahertz. And then after modification, it maxes out at like 3.05 or something. It's like, well, that might be because the second time you ran the card, it was running like 5 degrees Celsius cooler. And that is actually, depending on the architecture, that is actually enough to make that kind of difference, which is really, really annoying. So yeah, that's one of the reasons I really like having the oscilloscope, because you can actually see if the voltage regulation improved instead of trying to guesstimate if it improved based on, is there more overclocking headroom? Though at the same time, you can sometimes get like, oh yeah, there's less undershoot, but the card doesn't actually clock any higher. That I've also run into that scenario. Though that is usually because the undershoot reduction is like 10 millivolts, and that just doesn't really do that much to volt. Like, that just doesn't affect the clock that much, clock stability that much in the first place. So, yeah. Anyway, this is how the card behaves on like the stock VRM configuration. I think I can probably bring the peak down to like 200 millivolts peak to peak. That I don't think should be too difficult. But mainly what I would like to do is, we're seeing like minimums down into the like 970 millivolt range right now, with like an average of like 980-ish. So if I could get this to like stick closer to 1 volt instead of 980-ish, that would be great, I think. Well, that might actually lead to slightly better overclocking headroom, but yeah, we'll see, I guess. Like that's sort of the point of testing this out. Yeah, anyway, so that's it for this video. So I guess thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions if you comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with the channel, I have a Patreon. There's a link to that down in the description below. There's also the HOC Teespring store where you can pick up shirts, hoodies, posters, you know, the usual YouTuber merch. And I've also got a Bandcamp. There's a link to that down in the description below as well. So yeah, that's it for the video. Thanks for watching, and goodbye.